before the pause is Alexander Phraxos, who will speak about the future of biomethane in our hands. Welcome, Alexander. The floor is yours. Don't forget to unmute yourself, of course.
Hi, hello. Is everything looks good?
Yes, hello, you can start.
Good afternoon, and I really appreciate the opportunity to talk about the future of biomethane. It's time to take climate action to the next level. Only if we combine conventional approaches to climate mitigation with CO2 removals, the world might have a real chance of preserving our natural environment. In 10 years, we have to be capable of removing several gigatons of CO2 equivalent emissions, and in 30 years, tens of gigatons. Just to fully grasp the magnitude of scale, 1 gigaton is almost 2 times heavier than the total mass of the human population. Currently, there is a great deal of R&D on negative emission technologies. Nets take more CO2 out of the atmosphere than they put in. A widely discussed example is bioenergy with carbon capture and storage, also known as BECCS. In its most traditional form, BECCS relies on a supply of woody biomass that is combusted in coal-fired power plants. The CO2 in the exhaust gas is captured and stored underground. BECCS is a technology that oftentimes put forward despite limited feedstock supplies, complex logistics, coal phase-outs, and energy-consuming CO2 storage. In order for BECCS to realize its full potential, a virtually limitless feedstock, a technically scalable process, and CO2 utilization is needed. By switching the source of biomass from wood to seaweed and anaerobically digesting it to produce biogas is a great way of hitting 2 birds with 1 stone. Seaweed can provide immense supplies of feedstock, and anaerobic digestion is a highly scalable and climate-friendly process. In the biogas upgrading process, CO2 is separated from methane to produce a higher quality gas called biomethane. In a Sabatier reaction, the separated CO2 can be combined with clean hydrogen produced via renewably powered electrolyzers to yield additional renewable natural gas. Therefore, bioenergy with carbon capture and storage is transformed into bioenergy with carbon capture, utilization, and storage, fueled by macroalgae with seawide growth potential. By applying Industry 4.0 technologies such as the Internet of Things, robotics, artificial intelligence, and genetic engineering to seaweed cultivation and harvest systems, a largely automated and highly reliable seaweed farm could be built to both reduce costs and the risks of global warming. Large-scale industrial seaweed cultivation will enhance water quality by feeding on nutrients and CO2, hence mitigating coastal acidification. On a yearly basis, a seaweed farm the size of the Netherlands could provide enough proteins for the entire European population, and a seaweed farm the size of the United Kingdom could suck more than 2 gigatons of CO2 from the atmosphere. Imagine what's possible. Pyrolysis is a process of chemically decomposing organic materials at elevated temperatures in the absence of oxygen. The word pyrolysis is coined from the Greek words pyro, which means fire, and lysis, which means separating. Biomethane pyrolysis is a breakthrough energy positive technology with a carbon negative footprint. The pyrolysis of biomethane is a key step in the bioenergy with carbon capture, utilization, and storage process. Instead of burning the biomethane, capturing and storing the CO2 underground, biomethane is being pyrolyzed to yield hydrogen and highly valued carbon nanotubes. In other words, the C atom in biomethane is being converted from a liability into an asset. Today, hydrogen is enjoying such a remarkable momentum. The world shouldn't miss this unique opportunity to make hydrogen a significant part of our sustainable and secure energy future. As an example, hydrogen can play a key role in achieving the objectives of the European Green Deal and Europe's clean energy transition. Hydrogen has a myriad of energy and non-energy uses, such as storing renewable energy, generating electricity, fueling heavy transport, and providing energy and feedstock to energy-intensive industries. And most importantly, hydrogen offers a solution to decarbonize industrial processes and economic sectors, where reducing emissions is both urgent and hard to achieve. Furthermore, hydrogen is a clean energy carrier that can be seasonally stored and transported cost-effectively over long distances via the existing natural gas infrastructure. It is worthwhile to mention that a gas grid is much more cost-effective than an electrical grid. For the same investment, a gas pipe can transport 10 to 20 times more energy than an electrical cable. So, international cooperation is vital to accelerate the growth of clean and flexible hydrogen around the world. Recent research and technological advances have established a promising pathway for a class of high-grade solid carbons, namely carbon nanotubes. Carbon nanotubes are cylinders of one or more layers of graphene. Graphene is a special form of graphite that is 100 carbon and only one layer thick. The unique nature of carbon endows CNTs with extraordinary material properties, such as very high thermal and electrical conductivity, stiffness, strength, and toughness. Carbon nanotubes have been recognized as a wonder material that could revolutionize, among many others, aerospace, automotive parts, sports equipment, and building materials. Public-private partnerships, inclusive research and innovation, and techno-progressive decision-making are all key pillars to make carbon nanotubes the materials of the future. The current crisis has shown that new paradigms are necessary to drive the global economy forward. Thank you.
Thank you, Alexander. Thank you for this speech about the roads leading to hydrogen. I will take a look to see if there are questions at the moment. Yes, there is one from David Wood. What is the single biggest obstacle to scaling up the use of hydrogen as you describe? And I will also read the question from Cyril. I'm wondering if some study already estimated the optimal level of greenhouse gases in the atmosphere, because if we are really successful to decarbonate, I'm wondering if we may trigger a snowball effect, a real one, with too low greenhouse gases to keep the atmosphere warm enough.
Okay, so the main obstacles for that technology to be commercialized are how we can remove the carbon that is attached to the catalyst in the process of biomethane pyrolysis. Though the cost of producing hydrogen is much cheaper than doing it with electrolyzers. So that could be quite advantage for that technology and open up the doors for widely hydrogen commercialization. And then the other question was about greenhouse gases, that something about a snowball effect.
Yes, in short, if we can lower enough the level of greenhouse gases, it could be also too much. Yeah, so do you know about study to estimate the optimal level of greenhouse gases in the atmosphere?
Mm-hmm. So the optimal level would be net zero greenhouse gas emissions before the switch of the next century. Because we do know that if we remove now, for example, all the greenhouse gases, the atmosphere is a little bit slow to adapt to those changes. So I would say around 2000, between 2070 and 2090 would be a very good estimate and window that we have to become net zero.
Okay. Thank you, Alexander, again. If there are other questions, I propose that you answer in the chat. And now we have we stop for about 10 minutes. Well, we stop for 10 minutes. And Marion will show you 2 episodes of the same Symphony of Science, something already from a while ago, but